Hello everyone, today we will be discussing implicit differentiation. We'll find the derivative of a complicated function by using implicit differentiation, and we'll use implicit differentiation to determine the equation of a tangent line. So far we've been discussing functions that have been defined explicitly, that is, functions such as y is equal to something with x. Y is explicitly defined in terms of a variable x. For example, y is equal to 4x squared plus 5x. Now we can differentiate equations which are implicitly defined, such as xy squared plus 3x plus y equals 8, or even x squared plus y squared is equal to 25. How can we differentiate that? We're going to find out in this lesson. There's some functions that are implicitly defined, which we can solve explicitly for y, and then use the differentiation techniques that we have been using so far. One such example is that y squared is equal to x. We can define this explicitly by trying to solve for y, taking the square root of both sides. We could call one of these y sub 1, the other y sub 2, where y sub 1 is equal to radical x and y sub 2 is negative radical x. Note that this y sub 1 and this y sub 2, they're really just two equations in y. We could have said y is equal to root x and y is equal to negative root x, but this is just for differentiation of these. Does not mean that these are actually numerical values. They're still functions. Okay, so if we were to differentiate the y1 is equal to root x in a normal way for what we did with the explicitly defined functions, then what would happen is that we have the dx of y1 will become d dx of radical x, which if we did our differentiation using our power rules, we end up with 1/2 x to the negative 1/2. And if we did the derivative of y sub 2, again by using the power rule, we end up with negative 1/2 root x. So notice you have two different derivatives. One's positive and one is negative. There's a 1/2 root x and a negative 1/2 root x. However, if we were to use implicit differentiation to do this, we would follow a series of steps. We take the derivative of both sides of the equation as we normally do, rewrite the equations so that terms in dy dx is on the left side, and the other terms without dy dx are on the right side. Then factor out dy dx on the left side if needed, and solve for dy dx using appropriate algebra. For example, we to use implicit differentiation to solve the y squared is equal to x. We take d dx of y squared is equal to d dx of x. Then if we take the derivative, treat y here as a function of x, so we just taking the derivative as we normally would with the power. So we bring the 2 over and the exponent down 1, so that'd be 2y, but then you have dy dx equal to d dx of x is equal to 1. Taking the derivative of x is equal to 1. So then solving for dy dx, we have dy dx is equal to 1/2y, and this one solution is equivalent to the two solutions that we got when we did it explicitly. Okay, so let's do another problem. Determine the derivative of x squared plus y squared is equal to 25. So we have x squared plus y squared is equal to 25. Take the derivative with respect to x of each term on both sides. So that's d dx of x squared, d dx of y squared, d dx of 25. Okay? D dx of x squared is 2x. D dx of y squared is equal to 2y dy dx. And the derivative of a constant is 0. The rest is trying to keep the dy dx terms on the left side and everything else goes to the right. So we're going to do some algebra here. If we bring the 2x over, we have 2y dy dx is equal to negative 2x, and then divide in both sides by 2y, we have dy dx is equal to negative 2x over 2y, and then we can simplify that. Dy dx is equal to negative x over y. Now in the next question, we find that the slope of the line tangent to x squared plus y squared is equal to 25 at the point 3, 4. All you need to do is to plug in 3, 4 into this function. So under the derivative function. So dy dx at 3, 4, you plug in the 3 for the x, wherever you see the x, and the 4 wherever you see the y, and you're done. So dy dx at 3, 4, normally we have a line here and then put the coordinates here, 3, 4 down there. So that's the way for writing it. When you're going to plug in some coordinates, you put dy dx and then this line and then the 3, 4. So that's the way of writing it. Okay, so let's now do some other problems. Let's do this problem. Determine the derivative of x squared plus minus y squared is equal to 9. Derivative of x squared minus y squared is equal to 9. So x squared minus y squared is equal to 9. Again, we take the derivative of all terms. So that's d dx x squared minus d dx y squared is equal to d dx of 9. d dx of x squared is 2x. And from a power rule, bring that 2 over and take one exponent down. d dx of y squared is going to be equal to 2y. Treat it like a power, as a power rule, that's 2y, and then dy dx is still taking the derivative of y with respect to x. d dx of a constant is just 0, right? And then the rest is just doing some algebra, keeping the dy dx on the other side. So we have negative 2y dy dx is equal to negative 2x. So that's by subtracting 2x from both sides. And then finally, dividing both sides by negative 2y, we have dy dx is equal to negative 2x over negative 2y. And then simplifying that a little bit, dy dx is going to be equal to x over y. Okay? So there you go. Let's do another problem. Determine the derivative of radical x plus radical y is equal to 8. And then evaluate this derivative at the point 36. 4, the point 36, 4. So let's go. We have radical x plus radical y is equal to 8. We want to rewrite this as powers because it's easier to take the derivative of power functions. So rewrite it as x to the 1/2 plus y to the 1/2 is equal to 8. Then take the derivative with respect to x of all the terms in this expression. So it's going to be d dx of x to the 1/2 plus d dx of y to the 1/2 is equal to d dx of 8. Then go ahead and take your derivatives. Derivative of constant is 0. Derivative of x to the 1/2, that's a power function. That's going to be equal to 1/2 x to the negative 1/2 plus derivative of y to the 1/2, that's going to be 1/2 y to the negative 1/2, then keep your dy dx there. That's what we are intending to find. So then, just doing some algebra right here, we bring the 1/2 x to the negative 1/2 to the other side, or we subtract 1/2 x to the negative 1/2 from both sides. So we have 1/2 y to the negative 1/2 dy dx is equal to negative 1/2 x to the negative 1/2, and then divide both sides by 1/2 y to the negative 1/2, and then try to simplify that as much as you possibly can. The 1/2s cancel. Then we can rewrite this as a power function, or as this quotient as a product. And then just keep on rewriting. You end up with negative y to the 1/2 over x to the 1/2, and then try to write it back in our original form it will become negative radical y over radical x. We can leave it right there. And that's good. That's good. Okay, the next step, you want to find what is the value at 36.4. So dy dx at 36.4. Just plug in the 4 for your y in your 36 for your x. So we end up with negative 2.6, negative 1/3 as our final answer right there. Okay. We're going to do one final problem, which is a little bit more complicated. But we are going to do that in the next lessons. Anyway, thank you for watching. Please remember to like and subscribe, and see you next lesson.